Then our next invited speaker is Jyoti. She's a senior scientist from Microsoft Research. She currently works on improving the performance of Microsoft large-scale data-intensive clusters, for example, developing algorithms for optimum physical designs of production job pipelines. So she works on the research topic of query optimization, which is also her talk today. The floor is yours, Jyoti.
Hi, can you play the recorded talk? The reason is I'm sitting in a hotel, so
okay.
I think I had a conversation.
Okay.
So I was traveling today due to some official reasons, therefore.
Hello.
Everyone, I'm Jyoti from Microsoft, and today I will be presenting our work on Query Optimizer as a service. This work was done jointly with Alek Jindal and is in submission at Sigmod Record. Query optimization is a critical technology that is common across all modern data processing systems. However, it is traditionally implemented in silos and is deeply embedded in different systems. Over the years, query optimizers have become less understood and rarely touch pieces of code that are brittle to change and very expensive to maintain, thus slowing down the pace of innovation. In this talk, I will argue that it is time to think of Query Optimizer as a service in modern cloud architectures. As you all know, query optimization is the bread and butter of data processing engines for improving performance and reducing cost of user queries. It is now becoming a critical piece in modern clouds where there is no database administrator and where user expertise is minimal and lowering operational cost is important. We are seeing a lot of effort and investment in building advanced query optimization capabilities in systems such as Spark, Greenplum, Snowflake, Azure SQL, Scope, Spanner, BigQuery, Redshift, Amazon Athena, CockroachDB, among others. Unfortunately, the current approach to building query optimization capabilities results in re-implementing similar techniques in different systems again and again. For example, many systems, including Spark, Calcite, Greenplum, Snowflake, F1, SQL Server, and Scope have re-implemented cascades-style optimization. As a result, there is a lot of repeated effort to get query optimization right in each of these systems. Instead, we propose unifying query optimization capabilities into a common platform that will help serve the customers better by advancing state-of-the-art across the board. Apart from redundant effort across systems that we just saw, getting query optimization right just for a given system is hard by itself. This is evidenced by decades of research as shown in top left on improving strategies for query plan search, models for estimating query costs, and models for intermediate cardinalities and other statistics. In fact, most production systems have been hardened over the years based on countless user scenarios, performance regressions, and customer incidents seen by product teams over time, as shown in bottom left. This has also resulted in query optimizers turning into massive black boxes of legacy code that are not just hard to understand or tune, but something that the product teams are highly skeptical to touch or change significantly. Next, let us understand the cause of this problem. The heart of the problem in current query optimizers is the tight coupling of the optimizer within the query engine, which results in not only high development costs, but also making it hard to advance the query optimizer to fast-changing needs of the new query processing engines. Therefore, it is time to decouple the query optimizer from the query engine into a separate platform. This will help consolidate the efforts and advance the state-of-the-art rapidly. Our core philosophy here is not to build yet another query optimizer, but rather to externalize the various query optimizer components to an external service and look them up when optimizing each new incoming query. A key enabler for such externalization is the number of recent machine learning-based techniques to improve various query optimizer components such as cardinality, cost model, and query planner. These learning-based approaches could train over large cloud workloads and specialize for various database and workload instances. The learning algorithms and models can then accrue towards a common query optimization platform that can be shared across and developed much more rapidly. We have taken a series of steps in recent years towards realizing this architecture at Microsoft in Cosmos. I will walk through these steps in the remainder of this talk. Before I dive deep, let's understand the three main components of any query optimizer: query planner, cost model, and cardinality estimator. Let us start with query planner. The query planner explores the space of possible query plans for the given user query. The goal of query planner is to produce the cheapest query plan to execute based on the cost model. Next, let us understand the cost model. The cost model estimates the cost of a candidate query plan. It uses cardinality of each operator in the query plan as a core ingredient to estimate cost for each candidate query plan. In practice, cost models are highly sensitive components of query optimizer, which are typically tuned over some key customers or benchmarks and rarely touched henceforth. Any change in the cost model could not only take years in development, but are also hard to deploy due to the large and unknown impact on query plans. Next, let us discuss the cardinality estimator. The cardinality estimator estimates the output number of rows from each operator in the query plan. Cardinality estimators grow worse with larger query plans and black box nature of user-defined operators that are typically present in production workloads. Consequently, cardinality estimation is highly challenging and is routinely found to be off by orders of magnitude in production systems. Having understood the limitations of traditional query optimizers, consider an alternative service-oriented approach to query optimization as shown in this slide. The first thing to notice is the externalization of three main components of the query optimizer: cardinality estimator, cost model, and query planner, from the deeply embedded query optimizer to an external service. Additionally, the externalized components are hosted as learned ML models trained over the past query workloads seen by a given set of customers in a given environment. For each incoming query, relevant models are loaded to the query engine based on the patterns in the query. The query engine still contains its default optimizer. However, its components are overridden by learned models loaded from an external service. Next, let us discuss the advantages of our service-oriented query optimizer. Our approach is reusable. We do not introduce yet another query optimizer, but rather a practical approach for better query optimizer development. It's decoupled. Service-oriented approach is decoupled, yet completely integrated end-to-end. It opens up the black box to see how good different components are and identify the key components. It constantly improves the different components of Query Optimizer by leveraging machine learning advancements. It improves with usage. The system gets better with more usage on the cloud since more diverse training data becomes available. It is instance optimized. There is natural instance optimization for specific workloads and patterns, something which is desirable. It is scalable. The decouple approach allows scaling query engine and externalize optimization decisions separately. It is shareable. The hosted models and techniques are shareable across different databases or engines. It is debuggable. It is easy to debug and investigate the issue with respect to each of the components. It is easier to roll back for a specific customer. It offers accelerated software development life cycle. System developers can focus more on training the core Query Optimizer components independently, thus accelerating software engineering life cycle. Finally, it is future-proof. The service-oriented design makes the Query Optimizer future-proof for the scale, variety, and complexity of cloud workloads. In summary, service-oriented approach opens a new way to think about query optimization, bringing in several notable advantages of doing so. Next, I present a 7-step recipe for turning a query optimizer into optimizer as a service. But before that, let's understand query execution in a big data query engine. A query is written by the user who submits it. It is then compiled, optimized, scheduled, and executed, after which the results are returned to the users. Next, I will explain each of the ingredients in detail. First is creating signatures or hashes for every query sub-expression or subtree. In the figure on the right, I'll show 2 queries containing same signatures or hashes of query sub-expression. A signature captures a query sub-pattern whose behavior could be learned across the entire workload. Therefore, it is extremely lightweight featureization, which is useful given the sub-second end-to-end time spent in query optimizers. Second ingredient is telemetry collection. The query engine needs to emit signatures along with runtime metrics to telemetry. It helps understand query performance and helps build better cardinality and cost models. While emitting to telemetry, we need to preserve customer privacy by anonymizing any business sensitive or personally identifiable information. But wait, we are not emitting telemetry, which could be useful only for troubleshooting. Next, let us see how this telemetry plays an important role in Optimizer as a service. And you guessed it right. This telemetry collected is used for generating training inputs for machine learning models. The step involves extracting the telemetry into a tabular structure, imputing missing data values, denormalizing the data into a flat table that is more amenable to training, and applying data cleaning techniques to it. And how do our models look like? Our models are micro models or lightweight per signature models, typically linear models. Micro models are small in size, thus faster to train and easy to replace quickly. Micro models trade the generality of traditional query optimizers, wherein they had to produce the exact same behavior for every query and every customer with specialized behavior that is ultra local to a given customer and a given workload. That is, each customer can essentially have their own cardinality estimator model, cost model, and query planner customized for their workloads. Fifth is model lookup. For faster lookup, we load models by customers' query templates or signatures. Sixth is in-process scoring within the query optimizer. This helps reduce the overhead of making thousands of external invocations for model scoring. We load models in the optimizer and score them whenever needed. Seventh is overriding default optimizer behavior. This can be done by checking presence of available models. This is one-time deep change in existing query optimizers that is useful to control behavior from externalized service. Next, we describe a success in deploying Optimizer as a service architecture for Cosmos Big Data Platform in Microsoft. Sharing the same infrastructure with other query engines like Spark, SQL Data Warehouse is still an ongoing effort. In Cosmos, we have Scope Query Engine, which does batch processing in a job service form factor. It has massive workloads of hundreds of thousands of jobs each day, which are scripted by thousands of users, and they process exabytes of data. Workloads in Scope have recurring job patterns. An analysis over a large window of production workloads consisting of 67 million jobs, 4.3 billion subcompetitions or query subexpressions show that more than 75% of the query subexpressions are repeated. We leverage these repeating subexpressions for optimizing scope jobs by training micromodels over them as discussed earlier. If we look at cardinality estimation in scope, it could be off by orders of magnitude. This is due to user-defined operators that end up as black boxes for the query optimizer. Using the micromodel mechanism discussed earlier, we were able to achieve up to 6 orders of magnitude more accuracy. More details can be found in the VLDB 2018 paper. Cost models in scope have remained relatively static for several years. There was a significant effort to replace original cost model as explained in SIGMOD 2020 paper. However, it had gaps in terms of production readiness. The externalized architecture of Optimizer as a service provides a solid foundation for iteratively improving these approaches. Next, moving to externalized query planning. The Scope Query Planner consists of 256 rules, with 1/3 of the rules not enabled in any of the current workloads as described in the SIGMOD 2021 paper. Our approach to externalizing the query planner was to identify which set of rules makes sense for a query, thus steering its search space towards efficient plans. Additionally, multi-query optimization is an important part of the query planner. In this, I will explain cloud views and physical layouts in detail next. Cloud views is our approach to reuse common competition across queries. Consider query Q1 and Q2 at time T1. We notice same query subtree being used in both queries, identified by its signature. If we materialize this common competition, then we can reuse it at a later time point T2 in queries Q1 prime and Q2 prime. Results from production deployment over a 2-month window show the cumulative latency of the jobs improved by 34%, indicating better customer experience and lower operational costs. More details can be found in our ETPT 2021 paper. Physical layouts, for example, partitioning of tables, are important for avoiding expensive shuffles. In SMOF pipelines, which analyze telemetry from millions of Windows devices to derive business intelligence, we found more than half of the intermediate outputs end up being repartitioned or resorted on the same attributes in consumer jobs, thereby leading to significant operational costs. On the left side, we see production pipelines from SMOF. Nodes here indicate a job and edges denote a data dependency between two jobs. We notice 73% jobs produce files consumed by consumer jobs and 78% consume files produced by producer jobs. Not only Asimov, this producer-consumer graph can be seen in other workloads too, connecting diverse industries like marketing, energy, financial services, healthcare, hospitality, and manufacturing. And on the right, we see choosing the right layouts depends on all consumers. Producer job on the top produces a file which is repartitioned by consumer 1 and consumer 2 on the same column for different needs. At the bottom, we see our approach, which analyzes the consumers and decides to partition by column A that the producer should be creating to reduce overall execution cost of the pipeline. Next, let's discuss the risk and responsibilities for building a service-oriented optimizer architecture. Applying machine learning for building better systems has emerged as a hot trend in recent years. It is motivated by the fact that modern cloud systems have become too complex to optimize, coupled with ease of use of machine learning. Even though it makes sense to apply machine learning for building better optimizers, it is well known that machine learning also comes with its own set of dangers. The question is whether by applying machine learning for query optimization, we are importing those dangers as well. Next, I discuss some critical questions. The goal is to provide pointers and suggestions on making ML for systems more responsible, one that is more ethical, fairer, and considers the overall good of user community. Next, we dive deep into the question, are we serving all customers or are the rich getting richer? One of the biggest risks of using machine learning for query optimizers is that customers with larger workloads benefit more, since they can train better models to make optimization decisions. In contrast, the cloud provider has a responsibility to serve all customers, and so they need to devise techniques to transfer the learnings across. Therefore, the cloud providers still need to find mechanisms to democratize optimizer as a service for all players. The next question we ask is, are we enabling new workloads or are we penalizing the explorer? Customers who try new analysis risk creating diverse workloads that may not provide enough learnable patterns to optimizer as a service, thus penalizing exploring and rewarding repetitive work. The question then is how to incentivize explorers with good performance without asking them to become more predictable. Can we divide the workload into different portions and make a fair division? Next question we ask is, are we building better systems? Or are our systems opaque? By externalizing and replacing parts of the query optimizer with machine learning models, we risk substituting transparent, well-understood components with models that could be hard to explain or reason about. That is, are we leading to fundamentally better systems? Next, are we helping system developers or are we giving developers a hammer for every nail? Developers can easily fall into the trap of fixing everything in the system software using machine learning, bypassing better coding and system building practices in the first place. The challenge though is that they now need to maintain both the default-based system and augmented part of it in the optimizer as a service. At last, we ask if we are generating value. That is, are we learning versus improving? It is non-trivial to understand the improvements due to learned components beforehand. In fact, big improvements in accuracy may not translate to improvements in performance or other metrics. Therefore, much effort must be put in before the real value is understood or derived. Here, I show the references of the papers described during the talk. To conclude, in this talk, I opened up a fundamentally new debate in query optimization to build Query Optimizer as a service. Some key takeaways from the talk are the reference architecture of designing such a service, which is in production in Cosmos at Microsoft, and the risk and responsibilities associated with Optimizer as a service, which need to be introspected. Thank you.
Thank you very much for the wonderful talk, Jyoti. Now we open the session for Q&A.
I have a question if I can start. Yeah, so Jyoti, yeah, of course, thanks for the great talk. It's a very interesting idea. I was wondering a bit about how this can work with other database management systems. So, for example, it's indeed true that a lot of the code in query optimizers is there's a lot of overlap. But usually there is also some secret sauce that every system applies, and it might get its competitive advantage from this. So I was wondering if a database system would use this query optimizer service. The way you envision this is that this query optimizer service would return a query plan to a DBMS, and then this DBMS maybe could apply other techniques to this query plan. And before it executes the query, how do you envision it?
So that's a very good question. And it is true that every database has a secret sauce. But if we look at like within the organization that is in Microsoft, like we have like different query optimizers for different purposes. Now implementing the same query optimizers in like for different systems, it's like a huge, could be a huge loss for us because it's a lot of manpower goes in and it's the same things being implemented in different systems. So then it makes sense for us to like look into like something like an architecture like this, wherein like once we have like learned something in a system, let us say like Cosmos or Scope, we can then reuse it in like Azure Spark or Azure like SQL Data Warehouse or like other like SQL Server or other components. So instead of like re-implementing or reusing or reinventing the same things again and again in different systems. So it is like, all these systems, what essentially they do is that they emit the signature and the query plans, and then the machine learning models learns from it and learns based on customer workloads, and then injects the insights back, like, or learns the cardinalities, cost models, and the rules, and then sends it back to the query optimizer. But it's a very good question.
So as a follow-up question to this, because the cardinalities they can change depending on the data that I have on my database. So what is the information that I need to give as an input to the query optimizer service to keep on estimating the cardinalities and keep the cost model statistics up to date?
Right, that's another good question. So when we emit the signatures, we also emit the query plan and other like information about the data, like for about the queries. So that captures the cardinalities of the tables on which the queries are operated, etc., as well as, for example, other correlations which have been captured by, let us say, joins and other operators in the query plans. So in clouds, we have like large workloads. So they capture most of this information. So that helps us use them for like training and learning as the data changes. Does it make sense?
Yeah, I think so. I need to wrap my head a bit around it, but I think I get the main idea of how that can work.
Right. For example, for a given query, so what we do is that in addition to the query plan and the signatures, there are other like runtime metrics which are also emitted. So those runtime metrics do capture that how much data has been read from the tables, etc. What are the inputs to this query, and they would be like input tables. What were the statistics on those input tables that existed, for example, histograms, etc. And that can be used for like training the machine learning model for like cardinality estimates, etc.
I see. Yeah, thanks so much. Back to you, Rihan.
I also
have a detail just one small point. So for a detailed understanding, you can refer back to the cardinality estimation paper. So the VLDB 2018 paper that would like describe the detailed flow that goes through it. Yeah, go ahead. Sorry.
So actually, I also have a question. During your presentation, I see several parts of the query optimizer they are learned, for example, the cardinality. I'm wondering, in real production, when you have a lot of data, I assume all the machine learning part, like hyperparameter tuning, model selection, are all automated, right? So I want to know a little bit high level idea how you do this auto ML part, and how exactly do you get your training data in production?
So when the queries execute, so at that time, like as I was saying, so all this telemetry is being has been collected and that has been stored, and then we like go through a phase of generating the training input. So training input meaning that so that different machine learning models can operate on the same data, and we don't have to do all kind of data cleaning and other techniques again and again. So we generate this training input for all the training models, and then on that the models have been and on that the models train. For example, if it's cardinality estimation, then on that training input, the cardinality estimation model changes. Of course, the features are different for the cardinality estimation in comparison, let's say the cost models, or let us say the query planner. Does it make sense? So it is from the training input. So in the 7-step recipe, when it has one of the ingredients as collecting the training inputs from the telemetry that has been collected.
Then actually, after you running every batch of queries, will you also collect some of the statistics as the training data for next round?
Some of the statistics for the training data for next round. So the thing is that as I mentioned during the talk, so in Cosmos, most of the workloads are recurring in nature. So what we do is that we run some analysis over, let us say, a month, and then when new data comes in or when new queries comes in, then we run another analysis. So queries are of different natures. Some are weekly, some are monthly, some are hourly. So based on that, we keep retraining our models so that the models are up to date for each of the inputs. Does it make sense?
Yes, now I get it. Are there any other questions? Okay, then we can leave all this discussion also offline. Thanks again, Jyoti, for the wonderful talk.
Thank you.